Okay, we're going to talk about factoring expressions. And to factor an expression basically means that you look at an expression and you find that the terms might have a factor in common, and you can use the distributive property to factor that number out of the expression to create the form A times B plus C. I'm going to get into my drawing mode here. So we're looking to get it into this form. Normally, the number that gets factored out is the GCF. Now, we're going to just revisit the distributive property for a moment before we look at the factoring. When we looked at the distributive property, we basically said, okay, we can break a problem like 5 times 37 into 5 times 30 plus 5 times 7. So we would be distributing the 5 to the 30 and to the 7, and we would end up with 150 plus 37. I'm sorry, 35. 35. So when we're looking at factoring, we're basically starting with this expression and kind of going backwards to get into a form of the greatest common factor and what those were multiplied by. Now, in this case, is the greatest common factor 5? Like over here, we multiplied by 5. Is greatest common factor 5? Probably. Let's just see. If we take 5 and divide both of these by 5, yeah, we end up with 5 times 30 and 5 times 7. Can 30 and 7 be divided any further by a common factor? No, they can't. So 5 was the greatest common factor there. And this is now my A times B plus C form. So factoring is basically doing the opposite of the distributive property to get it back into this form where we could now say, oh, I can distribute the 5 to the 30 and the 5 to the 7. So they're closely related. Distributive property is used for factoring, but this is how it ends up looking. So we look at the expression, we try to find the greatest common factor, and then we divide by the greatest common factor to get this format. So for something like 15 plus 20, we can look at that and say, what can they both be divided by? We could list out all the factors. Some students will be able to look at this and say, well, I know they're both divisible by 5, and that's the biggest thing I can divide by. 5 times 3 is 15, and 5 times 4 is 20. 5 times 3 is 15, 5 times 4 is 20. So that's pretty simple. This one is also fairly simple. We do have a variable, and that's okay. It doesn't really affect how we're finding the GCF since there's only that variable. We look at the 4 and say, okay, 4 can be divided by 1 and 2 and 4. Some students might start with 2 and say, all right, well, I'm going to divide them both by 2. And this is a correct factorization. It is not the simplest terms, and it's not factored by the greatest common factor, but it would still be correct. 2 times 2 is 4, and the x stays there. So if I take this 4x, divide it by 2, I'm left with 2x. And then if I take the 24 and divide it by 2, I'm left with 12. Does that equal the original expression? 2 times 2x is 4x. 2 times 12 is 24. So it does equal the original expression. I do notice, though, that 2 and 12 can both be divided again by 2. And so I can see that the greatest common factor wasn't taken out here. The greatest common factor would be 4. So if I divide 4x by 4, I'm left with just x. And 24 divided by 4 is 6. And if I check that, 4 times x is 4x, 4 times 6 is 24. Both of these expressions are equal and correct factorizations for this expression. Now, this one is the most correct because it used the greatest common factor, but these are both correct. And if you were to say, ask students, are these expressions equivalent? Yes, they are. They should be able to identify the fact that they both do equal 4x plus 24. Now, I like to do factoring expressions with the ladder method. So if you already watched the GCF video, we talked about the ladder method. And I would set this up, and this ended up being very, very helpful for students once we started doing this because, listing out the factors was sometimes challenging, and sometimes they missed factors as the numbers got larger. But if we did it this way, it ended up being a little easier. So we look at the 10 and the 35. What can both of those be divided by? They can both be divided by 5. So we put the 5 out here. 10x divided by 5 is 2x. The x stays there. We didn't divide it by x. 35 divided by 5 is 7. Okay, can 2 and 7 be divided any further? No, they cannot. So 5 is my greatest common factor. That becomes my a in this format, a times b plus c. And then these factors just drop down into my parentheses, 2x plus 7. So 5 times 2x is 10x, 5 times 7 is 35, and that is my factorization. 36 plus 48. Again, students could list out all of the factors of 36. And a little tip there for them, if they're going to list out, you only really need to list out the factors of the smallest one and then check it with the larger one to see if you missed any or to see which ones work. All right, 36 and 48. I'm going to do ladder method again. I apologize for that. I do typically ask students to start with prime numbers just because we do prime factorization sometimes and it's easier to stick with the prime number idea, but they could actually divide by anything here. But 36 divided by 2 is 18. We're going to go with that. And 48 divided by 2 is 24. They also really like dividing by 2. They'll be like, can I divide by 2? Yes. And so they pick 2 all the time. 18 divided by 2 is 9. 24 divided by 2 is 12. Okay, now we can't divide by 2 anymore. So we have to see, can we divide by 3? Yes, we can. 9 divided by 3 is 3. 12 divided by 3 is 4. 3 and 4 have no more common factors, so I am done. I'm going to have to write it over here. My GCF is 2 times 2 times 3, which is 12. And then the 3 and the 4 drop into my parentheses, 3 plus 4. So this, when factored, using the GCF, is 12 times 3 plus 4. 12 times 3 is 36. 12 times 4 is 48. Next example, 20y minus 32. I'm going to start with 2's again. 20 divided by 2 is 10. Try to write smaller. I don't need the subtraction sign here. I just need that. And 32 divided by 2 is 16. I can divide by 2 again. 10 divided by 2 is 5. 16 divided by 2 is 8. Do 5 and 8 have anything in common? They do not. So my GCF is 2 times 2, which is 4. And my remaining factors go inside the parentheses. 5, oh, this was a subtraction problem, so we need to make sure it's 5 minus 8. And we can double check. I lost my y. 10y, 5y. Did you notice that I lost my y? And 5y. We don't want to lose the y. 4 times 5y is 20y. 4 times 8 is 32. And last, we'll do 12 and 18. There's no variable in this case. Actually, let's do this. Let's make this 12x and 18x. So you can see what happens if we happen to have a variable in both places. So I'm going to start with my number. I'm going to start with 2. 12x divided by 2 is 6x. 18x divided by 2 is 9x. 6 and 9 have a factor in common. They have 3 in common. 6x divided by 3 is 2x. 9x divided by 3 is 3x. And now, do 2x and 3x have anything in common? The 2 and the 3 do not, but the x and the x are in common. So I could actually divide both of these by x. 2x divided by x is 2. 3x divided by x is 3. And now in this case, my GCF is 2 times 3 times x, which is 6x. And my 2 and 3 go into the parentheses. And to check it, 6x times 2 is 12x. I did add the x's. And 6x times 3 is 18x. And that checks out. Okay, let me know if you have any questions about factoring expressions.